At the end of the last video, I asked you to look at this function, f of x equals x squared e to the x, and find the intervals on which this function was increasing and decreasing, which is going to be very linked to the intervals on which the derivative is positive and negative. So I'm going to calculate the derivative. So we're using product rule. We get the derivative of x squared times e to the x plus x squared times the derivative of e to the x. So that's going to be 2x e to the x plus x squared, and the derivative of e to the x is just e to the x. Okay. Now, that's my derivative. It's always defined, so I don't have any critical points from the derivative being undefined. So I'm going to look for where this thing is 0. So when is 2x e to the x plus x squared e to the x equal to 0? So this is going to be easier to do if I factor, and I'm going to observe that I can factor out an e to the x, but I can also factor out an x. So I'm going to have e to the x times x, and then times 2, plus if I factored out 1x, there's one more x here, is equal to 0. So now three things, e to the x, x, and 2 plus x are multiplying to give me 0, so one of them is 0. It's not e to the x. E to the x is always positive, so it's never 0. But I could have x equals 0, or I could have 2 plus x equals 0, which would of course make x equal to negative 2. So I'm going to draw myself a number line. I'm going to label that this is for f prime. It's a good habit to get into right now. So far, we're really just looking at the first derivative and its sign. But eventually, we're going to be looking at the second derivative as well. And so we'll have multiple number lines. It's kind of nice to have these things labeled. So I'm going to mark off my critical numbers, negative 2 and 0. And notice that divides the real number line into 1, 2, 3 subintervals. And I know f prime has a consistent sign on each of those subintervals. So I'm going to just pick a test number. If I plug in negative 3, now I find it simplest to plug into the factored form of the derivative. So just looking at the left-hand side here, this is the factored form of the derivative. E to the x is positive, negative 3 will be negative, and 2 plus negative 3 will be negative. So we've got a positive times a negative times a negative. That's going to give me something that's positive. All right, between negative 2 and 0, I'm going to try negative 1. E to the x is positive, x will be negative, but 2 plus x will be positive. So now we've got two positives and a negative. That makes this negative. For a number to the right of 0, I'm just going to try 1, positive, 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 positive. All right, so my function, f, is going up and then down and then up. So I can say that f is increasing on the interval from negative infinity to negative 2. Notice I'm including negative 2 because my original function was continuous, and when that's the case, we get to include finite endpoints where the derivative changes sign. Okay. So this union the interval from 0 to infinity. When there's more than one interval, we connect it with this u, which is just a union symbol. And you'll notice, again, I included that finite endpoint of 0. F is decreasing then on the interval from negative 2 to 0, including both endpoints. Excellent. So, now, just looking at these arrows that I've drawn on this number line, that really gives me some sense of the shape of the graph. It's going to go up and then down and then up. And what we're building towards is being able to graph a variety of functions that using just algebra we don't have the tools to graph, but using calculus we do. Notice I can see just from the shape of these arrows, there's going to have to be a max when x is 1 and a min when x is 0. I can see that just by the inspection of the shape of the graph. And in fact, we can formally state that as the first derivative test. This gives me a way of finding relative maxes and mins. They're not guaranteed to exist the way absolute maxes and mins are if we have a continuous function on a closed interval, but this gives me a way of checking for them. So the first derivative test says this. If c is a critical number for f, and f is continuous at c. So it is important that it be a critical number where the original function is continuous. Totally fine if it's a critical number because the first derivative is undefined, but we do need the first derivative, or the original function to be continuous. And if f prime of x changes sign at c, then c is the location of a max or a min. Okay. And I can know which one it is by basically looking at the graph. So if it's a max and I have my number line for f prime and my critical number c, a max is where we stop going up and start going down. So it would change from positive to negative. I'm going to have a min, on the other hand, if we change from going down to going up. So I can look at that picture to see. Now, that gives me the location of the max and min. If I want to find the value, that's asking how high up or down is the graph. To find that, I would just plug into the original function f. Okay. So remember, our original function f was x squared times e to the x. So I can say f has a relative max when x equals negative 2. That's the location. The max is f of negative 2. Plug into the original function, so I would get 4e to the negative 2, or 4 over e squared. Do be careful when we're finding the value of the max and min, we're going back to the original function. So for a while we were working with the derivative. Once we want to know the value of the max or the min, that's a y value on the graph of f. Okay. Similarly, I can say f has a relative min when x equals 0. The value of the min is f of 0, which is just 0. When I plug in here, I get 0. If you find that all your maxes and mins are 0, double check, you might inadvertently be plugging into f prime. But it is certainly possible for the value of a max or min to be 0, and that is the case here. Okay, so I'm going to give you another problem to work on, and we'll resume in the next video and look at it together. I want you to take a look at f of x equals the natural log of x squared plus 9. And I want you to find me the intervals where it's increasing and decreasing, and I want to find all the location and value of all the relative maxes and mins. Okay, one quick note before we pause so that you can work on this. Anytime I see the natural log function, I want to be conscious of what the domain is, because I know that the domain of the natural log function is just positive numbers. So the argument of the natural log, or the thing I'm plugging in, has to be positive. Well, since it's x squared plus 9, it is. So the domain in this case is all real numbers. But if this wasn't something that was always positive, I would have a restricted domain, and I want to make sure I was just working on that. Okay, see you in the next video.